The second topic, which is Kuratowski's theorem, let's start that. So our whole objective is to find out a set which is larger than the previous Venn diagram, right? So we need to check whether is there any such kind of set which is beyond the previous Venn diagram. So that we are searching. So the first question is the given graph is non-planar? Now the idea is we need to check whether it is a supergraph of K5 or not. So is the graph is supergraph of K5? So see the K5, I have also drawn that K5 graph by the side of the original graph, and we are seeing that the graph does not have 5 vertex each adjacent to other 4 like in K5. So in K5 we are seeing all the vertices are basically adjacent to the other 4 vertices, right? If you consider any vertex A, it is adjacent to all other vertices B, C, D, B, C, E and F. But if you see the first previous graph where every vertex is not adjacent to the other vertices, because if you see A is adjacent to B, C, E, F, which is correct. B is also adjacent to A, C, E, F, that is also fine. But C is not adjacent with A, B, C is adjacent with A, B, D and F. Since there is no edge between C and D, we cannot say that this is a supergraph of K5. So the answer is no, this is not a supergraph of K5. Now we need to check whether this graph is a supergraph of K33. Now let's see the diagram of K33. What we are seeing here is K33 has a 6 vertices and every vertex has degree 3. In our original graph we have also 6 vertices, but the problem is the vertex D has only 2 edges incident on it. So therefore D has the degree 2. So definitely it is not a supergraph of K33. So we can conclude that this new graph, what we are trying to cross check whether it is a planar or non-planar, it is not a supergraph of either of K5 or K33. So the graph does not have, so I have given the reasoning why it is not actually supergraph of K33. So the final answer is the graph is not supergraph of either of them. It looks like this graph is a planar, right? Because it is not a supergraph of any of the previous one, K55 and K33. Now the question is, shall we conclude that it is a planar graph? Do we need to think a little more before any conclusion? Let's try for that. Let us try to make the diagram more close to K5 or K33. So if I push this particular vertex D into the upper direction, then I see this is the graph. So it looks like similar to K5, but the only challenge is we have one more extra point D. Okay, it's still not a supergraph of K5, but it has some kind of similar orientation of K5, and it has some extra vertex on the line CE. But CE is not an edge in this graph, but CD and DE is the edge. So if we omit that point D, if we erase the vertex D and join the dangling edge from C and D, we get K5. So we can get the K5 like this way. Now the above process will never create a new edge crossing. So that we have checked that in the previous diagram, the process by which we have reduced our original graph G1 to K5, in that process we have not added any new edge crossing. So let's say we are assuming that graph G1 is a planar graph, and we have actually reached to graph K5 by certain process. Now in that process we have not added any new crossing, so which means if the original graph is planar, then the reduced graph K5 is also planar, but K5 is not a planar, that we have already seen. So whatever we assume, that is actually not true. So our original graph G1 is non-planar. So this entire process is known as actually the subdivision. So let's come to the definition of the subdivision. The subdivision of an edge E from U to V is the operation of replacing E by a path UWV where W is a new vertex. So to get a subdivision of E, introduce a new vertex W on E. Okay. Now a graph H is said to be subdivision of G if H can be obtained from G by sequence of edge subdivision. So if you look into the diagram, so we have in the left hand side we have a graph and E be an edge, let's say between U and V, and we have added one more vertex in between U and V, that is W, and we have deleted the previous edge UV and we have connected U and W and V. So we get a new graph which is basically we have created from the previous graph using the subdivision process. So the remark is, let's say if SG is the subdivision of graph G, then SK5 is non-planar, which we have proved. Similarly, we can prove that any subdivision of K33 is also non-planar. Now if we use the remarks which is given in the earlier slide, that any supergraph of a non-planar graph is also non-planar, then we can always say if H is a superset of SK5 or SK33, since SK5 and SK33 is already non-planar, so we can say the supergraph H is also non-planar. So this Venn diagram we have seen earlier. This is the supergraphs of K5 and K33, and we have already concluded that all the graphs inside this Venn diagram is basically a non-planar graph. Now we have defined a new process which is called subdivision. So so the left hand side diagram, Venn diagram, is basically a set which comprised all the member of subdivision of K5 and K33. And one more interesting point is in the left hand side, K5 and K33, since K5 and K33 are themselves subdivision of K5 and K33 are subdivision of themselves, so they are also the part of this entire Venn diagram. Similarly, since K5 and K33 are superset of themselves, so we have also included K5 and K33 in the right hand circle. So now we got two different circles, and we have proved the member of these two circles are basically these diagrams are basically non-planar, right? And then we have added one more rectangular on top of the left hand circle. So that what that rectangle is, the rectangle is the supergraph of subdivision of K5 and K33. And we have proved that if K33 and subdivision of K33 and K33 and K5 is a non-planar, so supergraph of that subdivision is also non-planar. So everything inside that rectangular box is basically non-planar. Now if you look closely, then we can draw this diagram. The reason is supergraph of K5 and K33 we have already considered in the previous diagram. See, in the left hand side, the rectangular box actually contains all the supergraphs of subdivision of K5 and K33. Since the subdivision of K5 and K33 itself contains K5 and K33, so it actually contains the supergraph of K5 and K33. So we got that larger set which is actually surrounded by this entire rectangular box. So what that rectangular box is, supergraph of subdivision of K5 and K33. Now, so we have proved that any supergraph of subdivision of K5 or K33 is a non-planar graph. Now let's come back to, let's go to the Kuratowski's theorem. It said that every non-planar graph is a supergraph of subdivision of K5 or K33. So it's the similar kind of, it's not exactly the same what we have proved. We have proved what? We have proved if I have a supergraph of subdivision of K5 and K33, we can say that is non-planar. But what Kuratowski's theorem is saying, if I have a non-planar graph, then definitely it will be a supergraph of a subdivision of K5 or K33. So if we, this particular proof of this entire Kuratowski's theorem is very tedious. So we have not included that proof inside our lecture note, but we can go to that any standard book like Harare and all. So we can, there we can find that the proof is little tedious and I have omitted for this discussion. So if we assume the Kuratowski's theorem and the last remark, that is, if H is supergraph of subdivision of K5 and K33, then it's non-planar. Then we can come to that corollary 1. What is that? The set of all non-planar graphs is equals to the set of all graphs that are supergraphs of subdivision of K5 or K33. It is just as in set algebra. If A is a subset of B, and which is given in the last slide, that the SK5 and SK33 is a proper subset of H, and here we found that the planar graph is basically a subset of supergraph of subdivision of K5 and K33. So if we combine both of them, we will get that set A equals to set B. So A proper subset B and B proper subset A, both of them imply to A equals to B. And we can rephrase the entire thing in corollary 1a. The set of all planar graphs is equal to the set of all graphs that are not supergraphs of subdivision of K5 or K33. Now, let's come to then one more very important topic, which is called as homeomorphism. Now, what is homeomorphism? So, I have drawn two different graphs. One is G, another one is H. Now, so these G and H, they are basically not isomorphic to each other, because we can see that G has a circle with 4 edges and H has a circle with 3 edges. So they are not isomorphic. Now, these two graph is not isomorphic to each other. So we have added some more subdivision on the original graph SG, and we original graph G and H, and we actually created a new graph which is subdivision of the G. So we have added one more point, and similarly we have added another vertex for graph H, which is a corner vertex. So, and now if we compare these two graphs, subdivision G and subdivision H, we can easily prove that they are isomorphic, right? So two graphs SG and SH are isomorphic to each other. The original graph G and H, they are not isomorphic, but the subdivision of graph G and subdivision of H, they are isomorphic. Now let's come to the concept of homeomorphism. Two graphs G and H are homeomorphic if there is an isomorphism between subdivision of J and subdivision of H. So we are not bothering about G and H, but what we are bothering is whether the subdivision of G and subdivision of H, if they are isomorphic, then we can say it's a G is homeomorphic to H, or G and H are homeomorphic. Okay, so if we now, based on this definition, we can state the Kuratowski's theorem in an alternative way. A graph is a planar if and only if it contains no subgraph homeomorphic to K5 or K33. Now, so what we have learned as of now is, we have learned that the superset of subdivision of K5 and K33, both are actually non-planar. So whenever we find a graph, what we will be trying is, we will always try to find out whether is there any subgraph which is subdivision of K5 or K33.